Hi guys, today we are going to go through the notes for section 2.3. It's the last section of chapter 2. Then we'll be moving on to chapter 3 and we will be having our big chapter 2 test soon. Remember those vocab terms that we did yesterday? Will be on the actual chapter test. You will not have a vocab quiz on just those terms. So I'm doing the notes a little bit differently this time since we are probably back in school. You're going to start taking actual notes. And instead of doing the guided notes like I used to do, I used to have things where you would just fill in a couple words or write a couple sentences. I'm trying to not use paper as much so that we don't have a transmission of germs back and forth. So I'm going to make assignments on the Chromebook as well as I can, or to the best of my ability. Every now and again, yes, we're going to have to use paper. But for those of you who are learning remotely, you're going to be doing things solely on your Chromebooks, and you'll be submitting things to me that way. So up to this point, you guys were being given participation, I'll say participation points, just for attending the lessons and for completing the assignments as we went through them. I used to do something called a notebook check, which would have been all of your vocab sheets and all of your notes. I would have taken those, and as long as you had them filled out, you would have gotten points for that. And I'm going to try to do a modified version of a notebook check just for the rest of this 9 weeks, and we'll see how it goes. I'm sure we'll have to tweak things as we, hit different speed bumps. So what I'm doing this time, I have color-coded different slides or different parts of different slides. And if you see the color blue, that would be something that you would need to write down, or in this case, type up. So do you actually have to have a notebook? No, because I'm not going to be collecting any of your notebooks, but you will be submitting things to me online. So, for example, if you look at this slide here, you would be writing down those 3 points there. So why is water polar? And I will have an assignment created where you will be uploading the document of your notes. So you're going to type out anything that you see in blue. I'm going to go to the next slide real quick. If you notice this slide here, this is black. You don't have to type that out. You're only typing out the stuff that you see in blue. So if I go to the next slide, oh, here's blue, you're going to type that point. And I'll be looking for those whenever we go through our notebook check. Okay, so let me try this and we'll see how it goes. So why is water polar? Well, there's a couple different reasons. The first one is because electrons are shared between oxygen and hydrogen, which creates a covalent bond. The oxygen is a bigger atom, so the electrons are going to spend more time around the oxygen. This is going to make oxygen slightly negative. And because those electrons are pulled towards the oxygen, that means that hydrogen is going to be slightly positive. So that slightly positive, slightly negative charge is going to be giving water this polar idea. A little bit background on water. Our bodies are made up of about 65% to 72% water. So a lot of you is water. That's why it's really important to stay hydrated. If you're not hydrated, it can lead to muscle cramps and spasms. It can also make you feel a little bit dizzy, so really make sure you're drinking water. Little overview of water here. A polar covalent bond is going to hold the hydrogen and oxygen together. Now, you don't have to draw this. If we were doing our notes, you would, but since you're just typing, only worry about this bullet point here in blue. So there are our polar covalent bonds. They're right between the hydrogen and the oxygen. There are 2 of them. A hydrogen bond is going to hold adjacent water molecules together. So this is in blue, so you would write that bullet point there. So this is where the hydrogen bond is. So you have a full water molecule, another full water molecule. Hydrogen is going to bond to oxygen. That's a hydrogen bond. This hydrogen is going to come in and bond to the oxygen, another hydrogen bond. Now, hydrogen bonds are super weak bonds, extremely easy to break. So we have covalent bonds within a water molecule and hydrogen bonds holding water molecules together. So would this be a possibility? Would you be able to have one water molecule hydrogen bonding to another water molecule from the hydrogens? Now remember, hydrogen has a slightly positive charge. Have you ever had 2 magnets and you tried to shove both of the same poles together, both positive poles together, you can actually feel a tension there. It doesn't work. Like forces are going to repel and go in opposite directions. So in order for this water molecule to bond to this water molecule, it's going to have to flip itself around 180 degrees, and the hydrogen is going to bond to the oxygen. Now, we said water is the universal solvent back in section 2, and it is. Most things can be dissolved in water. I didn't go into a whole lot of detail then, but I'm going to talk about it now. It's because we can have an ionic compound, which is a compound that is composed of two ions of opposite charges, positive and negative. These are full charges, not partial ones like we saw with the covalent bonds. So water can dissolve ions, which is an atom that has a completely positive or a completely negative charge. So if we look at this sodium atom here, it has an electron out here. Remember, we want to get to a perfect 8, so it is either going to have to find 7 other electrons out there, or it could just kick this electron off. Say, goodbye electron, I don't want you anymore. And that would leave it to have 8 in its outermost shell. Because it is getting rid of one, because it is getting rid of one of the electrons, it is now going to have a positive charge. So water can dissolve polar substances and ionic substances, but it cannot dissolve the fats, which are considered non-polar substances. This is like oil. Solubility is the ability of one substance, the solute, to dissolve another substance, the solvent. Now we're talking about some lipids here. Lipids are fats, they're oils, they're non-polar. They're described as hydrophobic, which means that they are afraid of water. The prefix hydro means water, phobic is a fear. So if you are afraid of spiders, that's arachnophobia, like me. Or if you are afraid of closed-in spaces, that's claustrophobia. So this is in blue. Make sure you write that down or type that out. If you take a look here at this picture, it says why oil and water does not mix together. It is because water is a polar substance, oil is a non-polar substance. So those two little words there kind of make water and oil unable to mix together. And you can see there's a very nice layer there where you could attempt to mix these up and they will immediately separate. Non-polar things do not like water. So how is salt dissolved in water? Well, when salt is dissolved in water, the sodium and chlorine will just break apart. These individual atoms are then surrounded by water molecules. So think of it like sharks descending on their prey here. We have the salt, and it's just hanging out there. You've thrown it into the glass of water. Maybe you have a sore throat, so you're gargling with salt water. These red ones and white ones, these are all our water molecules. So if you notice, the oxygen has that partial negative charge. It's coming in here to attack the sodium, which has a positive charge. The hydrogens, which are partially positive, are going to be attracted to the negative charge of this chlorine. So they are going to just attack this salt molecule. And eventually they will pull it apart, and now you can see there is sodium over here, chlorine's over here. We no longer have individual salt particles, but now we have salt water because it is completely mixed in. Properties of water. There are a bunch of different properties of water. Water is an amazing thing. The first one is cohesion, which refers to water's attraction to other molecules, other water molecules. So if you've ever had a little droplet of water, you could even do this at home, get some water and flick it off your fingers onto the table. You'll notice that the water is going to beat up, and you actually see water molecules, if they're close, they'll move closer together. That's cohesion. Water likes to be connected to water. And down here I have a water strider, and he can walk across water, which is kind of cool. He can walk across water because of surface tension. Surface tension is the strength of hydrogen bonds between water molecules on the water surface. Remember, you're writing down the part in blue, the black part you don't need to worry about. So a while back, these guys, it was another company kind of like the North Face. But this company tanked. It went under real bad. And they put out a video that showed guys in their shoes and their gear, and they were able to run across water. And eventually, they would just kind of fall into the water, but they could take a few steps. So here's this guy. You can notice he is running across the water. Now, the one problem with him being able to just run across the water like that, you can see all the water particles being kicked up behind him. So he is breaking the surface tension across that water. As soon as you break the surface tension, you are going to fall in. So if he were able to walk on water, he would have looked something like this water strider here. You would have seen it kind of like an indentation. You would not have seen droplets spraying all over the place. So it came out that this ad was really phony, and the company ended up not making it, unfortunately for them. What they had done was put a plank underneath the water, and they would just end up running right off the plank. It was a cool idea, I guess. Oh, have you ever done a belly smacker into the water? Do they not hurt? That's because of all of the hydrogen bonds that you are breaking in the water. So surface tension is kind of a strong thing. If you have a bunch of water molecules together and you just hit them flat on or straight on, it's really going to hurt. You will break the surface tension, but it takes a second, which is why you end up all red and you probably knock the wind out of yourself. The second property of water is adhesion, which refers to water's attraction to other substances that are not water. So, for example, it would be like water sticking to your clothes. I remember whenever I was outside years and years ago, walking to and from the bus, and if it was raining and I had jeans on, the bottoms of my jeans would be soaked because I stepped in water. But that water would actually trickle up, and half of my calf would be covered in water because the adhesive properties of water sticking to my jeans. So here I got Shamu, and they still do a little swim with the orcas if you go down to SeaWorld in Florida. They have a splash zone there, so whenever he splashes, all that water comes out and it sticks to your clothes. That is because of adhesion. So cohesion, you can see the water particles are actually sticking together as they fly out. And then adhesion is it sticking to your clothes. So these two properties work very closely to one another. Capillary action is water's ability to travel through a narrow space against gravity. So if you put a straw into the water, you will notice, or any liquid really, you'll see a little bit of that liquid kind of creeps up the straw some. That is that liquid using capillary action to climb up. Over here, if you look at these plants or this tree here, water is going to be moving up through the trunk to get out to the leaves. That is through capillary action. And here's a little bit of a better picture. The xylem and the phloem, that is inside of a tree, and that is water. That's how water moves from one cell to another cell using capillary action to get all the way up to the very top. The next property of water is that it has a high specific heat. So it takes a lot of heat to change the temperature of 1 gram of water by 1 degree Celsius. So if you have a pool and you've had a couple nice days, you're just getting ready to open it up, that water is going to be really, really cold still. It takes a while for water to warm up. This is really good for us because we're made mostly of water. And if we didn't have that high specific heat and we went outside on a 90-degree day, we'd probably sweat out all of our water and we'd be extremely dehydrated. But because it takes water so long to warm up, we get a little extra time before we start sweating to death. So it's easy regulation of body temperature for us. Oh, they're actually starting to come out with thinking that dinosaurs may not have been reptiles, but they might have been actually warm-blooded. They're thinking this because, reptiles have to be out in the sun in order to heat up their bodies and, maintain body temperature. But some of the really big guys didn't need that. So they're starting to believe that they may have been, warm-blooded. Here's that T-Rex. All right, one of the last things here is density of water. So what is unusual about the density of water? Well, solid water, which is ice, is less dense than liquid water. This is because the distance between the water molecules is larger in ice. So those water molecules will actually spread out the colder that they get. That's kind of crazy because most of the time a solid is going to just sink to the bottom in water. Solids are typically more dense than liquids, but with water it's not true. So that is why we can have our polar ice caps here where they are floating on top of the water, even though they are in solid form. And that then allows, bears to walk across them. Since ice is less dense than liquid water, it is able to float on top of the water. I have a picture of frozen vegetables here. Sometimes they're just easier to make, right? But if you were to compare a frozen vegetable to a fresh vegetable, the fresh one is going to be a lot more crunchy. The soft one is normally a little bit more flexible and bendy. That is because the water is actually getting inside of the plant. So it would get inside of this green bean or this pea, and whenever it expands, when it freezes, it's going to push out against the cell wall and actually pop that cell wall of that plant. So that's where all that crunchiness comes from. It's the cell wall. So whenever that cell wall gets pushed out against and popped, now you're going to have a vegetable that is not so crisp. Which is basically what I just said here. Because ice forms inside the plant cells, the cell walls of the plant will burst. The cell wall gives the plant its crunchiness when you bite into it. And that is it for the last section here. So we're going to do a little bit of practice with water and using those concepts, looking over the properties of water, and then we're going to have our Chapter 3 test next week. So if I were you, I would start looking over my Section 1 and Section 2 and Section 3 vocab terms and notes because you will be seeing them again. Alrighty guys, until next time.